Recorded and it's rolling. It is Friday, November 8th. Here's top scientist for circular motion gravitation orbits quiz. So I have not handed this back yet. One main reason is I'm still waiting on a bunch of late quizzes. So here's what I got late as of this morning. Well, for AP, I'm still waiting on 9 late quizzes at this point. So got to get this in for I hand it back. Right, and then of course when I hand it back, I'll also put the answer key for you guys, and then you can do corrections if you like. Right. Right. But if you're on this list, then you're doing pretty good. So awesome if you're on this list. All right. So yesterday I had you guys do that potential and maximum speed lab to get for reuse and conservation of energy, right? Potential to kinetic. Right. Most of you guys turned that in. Right, but I'm still taking it. See some of you guys turning in this morning, so that's good. Get that in the grade book. All right. Energy table. You guys got your energy tables out, the 3-page energy table. Let's see if we can finish those today, and then we'll see how much time is left for, well, always have those things queued up. All right. I think yesterday I told you guys to go watch Mark Gruber Pinewood Derby. I posted the link for that. So here, just anytime next few days. If you haven't watched it yet, then watch it sometime next few days. Because again, it goes through a thought process that's like exactly what we're doing in class. So you watch this video, like, oh man, that's like exactly what we're doing in physics class. Tells you how to create ideal Pinewood Derby car, thinking in terms of conservation of energy. All right, guys, AP Classroom. So as of this point in class, we have covered all the topics we got to cover for energy. I mean, we're still going to take next week and do some energy. I still got some labs lined up, still got some other activities. But guys, I want to go over the answers with you guys on Wednesday. So can you guys have this done by Wednesday morning so you guys come in and then we can go over the answers to AP Classroom? All right. Yeah, so I read all the questions. I think you guys should be able to answer all those based on, we've covered all the content. Okay. Of course, Monday is Veterans Day. There's no school. Tuesday is FCLE. All right, so guys, Tuesday, you might be taking the FCLE. If you are, then there is a file posted to Google Classroom. I think I posted it 2 days ago now. Shows where everybody's testing. Oh, yeah. Florida Civics Literacy Exam, I think it's called. Right. Guys, check that. If you're not sure, check that Excel file that I posted and see if your name's on it. If it is, you're taking it. It says exactly where you're taking it. Right. If you're not taking it, then well, there's an exam in this classroom. I'm going to be proctoring, so my first few classes relocated. All right, so you guys know relocated. This is for Tuesday. Okay. All right, Tuesday as well. All right, you guys got that? All right, everybody got that. All right. All right, so you guys ready to go with 3-page table? All right. So point. All right, so we're back to this table. You guys got this table out? All right, so the last I think the last one we completed was this bungee jumper. Right, we're thinking about the cord being like a spring. Okay, we finished that. Right. The universal question on this table is what's the speed at point B, and that was of course 0 meters per second. Right, all the energy went into the cord, like the spring. Think of it that way. Right, but guys, you could set up this conservation of energy equation here. You could say this plus this equals this, and then you could solve for something else, like how much did the spring stretch? Right. I forget if I mentioned this the other day, but this bungee cord question is really inspired by, there was an AP free response question that was almost exactly this. Actually, it was a little more complex because I forget, but it's like if you start with this and then they had like one twist on it, made it slightly more complex in this question, right? Right then, I think we had started on this Atwood. There's a couple of Atwoods here. So we got this modified Atwood here. Oh, yeah, you guys did a lab a few weeks ago that was Atwood. Now, just to remind you guys, what was the difference between a few weeks ago Atwood versus these Atwoods here? Guys, a few weeks ago, I had you guys figure out what's the acceleration based on the masses. That was pretty much the whole lab. What's the acceleration based on masses? Now, once you can figure that out, you can answer other questions. You can go back to kinematic questions. Say, well, how far has it fallen as a function of time? Or how fast has it fallen as a function of distance? You could answer all those. Okay? Now, if you specifically see the question, how fast is it moving as a function of distance? Then the fastest way to answer that question is with conservation of energy. And so here, this one's a little different than the table, but that kind of goes over, right? Because you guys see this conservation of energy setup? Oh, this h is the distance fallen, and this v is the speed. In fact, all these blocks would have the same speed. They're all tied together, right? So guys, if you ever see that question, what's the speed as a function of falling distance? You have 2 possible ways to answer it. You could solve for the acceleration first, then kick back to kinematic motion. Or alternatively, you can just do conservation of energy. You don't even need to solve for the acceleration for any part of this, right? All right, so here was really good. All right, here's the classic I-would, which we're about to get to. All right, but I think we had set up this equation the other day, and then the bell was ringing. So we said, okay, the fact that the block hanging over the table edge can fall, that's supplying the potential energy. And as it falls, it's losing gravitational potential energy. Okay. And where's that energy going? Well, it's going into the motion of each of the blocks. It's given on 1/2 mv squared. Right. So you got that, right? Right. So we just got to solve this. Got to finish this out. Maybe you guys already solved this. So here's the framework. Sum of energy initial equals sum of energy final. Okay. The large block falling, that's M2GH, is supplying the potential energy. So that goes into kinetic energy. 1/2 mv squared plus 1/2 mv squared. Okay. Now these are different blocks, block 1 and block 2, right? But they are the same speed, right? That speed and that speed, is that the same speed? Yeah, because they're tied together, right? No, different directions, but that's good. Do you guys notice here? Do you guys notice that direction of motion doesn't really matter so much for this topic because we're talking about scalar quantities, right? So these velocities would be different directions. That doesn't matter, right? And also, I've never really mentioned time so much as a variable for the past couple weeks. So, unless we're talking about power. But, all right, so solve here. I guess I can multiply everything by 2, right? Guys, how many different terms do I have algebraically? 3 terms. So if I multiply by 2, I have to multiply all 3 terms by 2, right? So I got 2 m2gh equals m1v squared plus m2v squared. Ooh, guys, could I factor this v squared out of this right side? Factor the v's. So that's gonna go like 2 m2gh equals m1 plus m2, and then v squared. That right? Right. Then divide down the sum of the masses, and then the last step is take the square root. Right? Can I do both those algebra steps? Okay. Skip a little bit here. So v equals, okay, the last step is going to be a square root. Okay. Now, what's the square root of? Well, I got this 2 m2gh. And then down here, I got m1 plus m2. Okay, the square root of all that right there. Okay. Right. Is that what you guys got too? You guys got that as the answer? All right. All right. Good news if you got it, because I think it should be it. Right. Guys, when you drew your square root bar, you did extend the square root bar over the entire inside expression. And you guys see, also, did you guys make it tall enough that it covers the entire fraction too? Right? Like, guys, you didn't do that. Here, I'm going to do something wrong because I've seen this year over year. Like, I've seen this like, oh, we got a square root. We got a 2 m2gh over m1 plus m2. Guys, is that right? No, guys, I've literally seen lots of students draw the answer like that. Guys, this is not this. Okay, so this is okay, so you guys are writing it like this, right? Okay. All right. Another thing to do too, like once you get an answer, is look at that answer and think, what does this mean? Like if you play around with the variables, like guys, as you make this M2 heavier and heavier, like more and more massive, gets heavier and heavier. Right? What do you think that's going to do to the overall speed by the time it drops that distance h? Should make it go faster, right? Yeah, I can kind of see that here. If you make this M2 heavier, like proportional to this M1, like if M2s get bigger and M1's not changing, right? Oh, actually, that's an interesting thing too. Because what if M2 is like 1,000 times bigger than M1? Guys got that? What if M2 is like this guy here, and M1 is like a little tiny paperclip? Okay, you guys got it. Okay. What would the speed approximately be after following distance h? Would that almost be like Galileo dropping a ball off the tower? And what was that answer? Square root 2gh. You guys remember square root 2gh? Right, all you have to do is flip back a page to Galileo. Okay. Hey, I wonder if this answer would be consistent with that. Let's see if it is. So did I just say M2 is like 1,000 times M1? So this M1 is basically approaching 0, right? Right. So basically, it's so tiny, it's like a little paperclip, right? And then so if you let that approach 0, this M2 over M2 could go away. Hey, look at that! Look what's left on the board. It is square root 2gh, isn't it? Look at that, right? Or you could go the other way around. What if M2 is a little tiny paperclip and M1 is like, hey, I'm on the top now, this big guy, Right, so M2 is a little paperclip. What would do you think it would take like 1,000 years for this to fall at distance h? And by the time it does, it's going really, really slow, right? Probably very close to 0 meters per second. Let's see if that's true too. So now I'm making M1 really big, and I'm taking M2 and making it tiny, tiny, tiny. Okay, so the numerator goes to almost 0. This denominator is really, really big. Square root of that, yeah, it would be a tiny number, wouldn't it? Right? You guys see how physics plays that like that, right? You can read the music of these equations, right? You see? Right, so that makes sense. All right. All right. So you guys have the answer here. Right, you guys, of course, writing something in this little box here. Classic Atwood. Where's my? Oh, here's my classic. I mean, this is the answer, right? You guys, you see this is the answer. Let's just look at this. Right? So, the fact that the large block can't. I think we went over this one yesterday. The fact that the large block can fall. That's like supplying the gravitational potential energy, right? And that energy goes into 3 places. You have to lift the small block. So boom, that shows up there. And also at the end of that motion, each of these blocks has a speed, hence a kinetic energy, right? Like in energy terms. So some number of joules, 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 right? So that's the setup. So here, I'll call this the M1, M2 Earth system. Right. Got M2GH is falling, and then it has to lift block 1, so that's M1GH. It's like supply of energy, demand for that energy. Right. There's also a plus 1/2 M1V squared and plus a 1/2 M2V squared. Okay. Oh, hey, is this V? This V? Is that the same V? Yep. Okay, now one's going down, one's going up. It's the same speed. They're tied to that same string. So got to solve that now. Solve that V. All right, so we got sum of energy initial equals sum of energy final. Our closed system, conservation of energy. Okay, got M2GH falling equal, all right, M1GH rising plus 1/2 M1V squared plus, ran out of paper there, plus 1/2 M2V squared. Okay, there's the setup. Okay, we're solving for this V right here. Okay, so I better probably subtract over the M1GH. Okay, so it looks like this M2GH minus M1GH equals, and on the other side I got 1/2 M1V squared plus 1/2 M2V squared. There. Okay. I see some things in common on the left side and also the right side. Like on the left side, the G and the H are common. On the right side, the 1/2 and the V squared are common. Right, so take some stuff out. Right, there may be different ways to finish this off algebraically. Right, so maybe I'll do M2 minus M1 and then pull the GH out. I mean, it's just kind of how you want to finish this off. Okay, I can pull out a 1/2. I can pull out an M1 plus M2 and then V squared. That's the same thing, right? Same thing. Right. Let's see. Times 2, divide by the sum of the masses, take the square root. I'm going to do those last 3 algebra steps right here. I think you guys can jump to that, right? So times 2. Right, okay, so V equals, what is V? Okay, so this expression right here, M2 minus M1 GH. So I got that down. Cross multiply this 2. Divide down the sum of masses right here. M1 plus M2. And then last step is take the square root. So square root of all that. Yeah, I think that makes sense. Look at that. The further it's following, the faster it's going. The more the gravity field, the faster it's going. Hey, difference over sum of masses. You know, I think that kind of checks out. Right? You could plug in individual values, see if it works. Right? How about this? What if one mass is crazy more massive than the other mass? What if M2 is like 1,000 times mass 1? Because if M2 is 1,000 times mass 1, isn't mass 1 approaching 0 proportionally? Right. Let's let M1 go to 0. Let's see what happens. Let's go to 0. Let this go to 0. Does that leave you with M2 over M2 here? Which simplifies to what? We have basically 1. Right. And then, hey, look what you're left with. Square root 2GH again. Look at that. Square root 2GH. Shows up again. Right. That's for to an extreme case. Yeah. So I think these are all working out. These are all working out. That's doing good. All right, next one. Ooh, got a couple of springs lined up. So this one, a ball falls vertically onto. Sorry. the spring fires the ball vertically to its maximum height. And this one is a block that's going to fall down and squash a spring, something like that. Now, there's a little bit different ways you can interpret these, so I'm just going to pick an interpretation and go with it. Okay. Also, I should say this. Oh, do you guys see here? These two are really similar, so we're kind of looking at both these at the same time. Do you see this in parentheses says assume no mechanical energy loss during collision? Is that's a note about something we have not talked about yet in this class. It's actually the next topic we'll get to a couple of weeks from now. Whenever you see collisions in physics, it's like two blocks colliding. In this case, maybe a block colliding with a spring, something like that. The way to solve collisions is through conservation of momentum. Momentum is mass times velocity, which we're going to go back to vectors. Yeah, that's going to be a couple weeks from now, right? But whenever you have a collision with a spring in a physics 1 class, it's really common to say, well, let's assume that the mass of the spring is tiny, it's a negligible mass compared to the block. And so you assume exactly this assumption, that there's no mechanical energy loss, right? So you don't do the collision physics for colliding with the spring, right? That's a common thing you do. All right, so we're just going to go through conservation of energy. Just think ahead a little bit. All right, so what could be in the closed system? What do you guys put in the closed system? The what, and what? The ball, the spring, and the earth. Exactly. Ball, spring, earth. Right. That will create a closed system. Right. The ball, because see, it's changing its motion, changing velocity, so it's changing kinetic energy. The spring, because energy was in the spring at some point, there was spring energy. And the earth, because there's a height change and a gravity field. Okay, so that will close the system. All right. Energy at point A. Guys, all the energy was in the spring. 1/2 kx squared. Oh, I should have done a review with you guys. You guys remember you're just pulling off this checklist right here, right? Okay, so spring. Okay. And you guys said 1/2 kx squared. Okay. Because that's the energy stored in a spring. Right. Then the ball goes to its maximum height. What's the energy there? mgh. Yeah, mgh. Right. All right. So if energy is conserved, can you throw an equal sign here? Say that number of joules equals that number of joules. Yeah, you can solve that way, right? Okay. Actually, that's that kind of reminds me of a short lab I wanted to do with you guys probably next week. Right? Have these little do you guys show you guys these little poppers the other day? Right, pull this inside out, let it go. Right, that's kind of like a spring going to its maximum height, but kind of setup right there. Right. So right there. Guys, what is the speed at point B? Yeah, 0 meters per second. Right. So probably not the ideal question. The ideal question might be like, how high does it go? Maybe that could be a better question. Right? I could have you guys solve for h. You just take 1/2 kx squared divided by mg. You do that, right? Next one, a block falls from some height and squashes the spring. Right. So is this still well, I don't know if I changed the word block. Oops. I guess we got a block. I guess it's shaped like a ball somehow. Okay. And we got a spring and we got the earth. Right. So same objects in the system. Is what kind of energy at point A? MGH, gravitational potential energy. What kind of energy at point B? Yeah, 1/2 kx squared. There you go, 1/2 kx squared. Right? I can say equals there. Okay. And that's a spring potential energy. And what's the speed at point B probably? Yeah, that's a good assumption. Probably 0 meters per second. That would be reasonable to say. Okay, so here's gravitational potential energy. Here's spring potential energy. I forget if I mentioned this. If I did, I may have said it once. Is that if AP ever just says potential energy out of context and they don't specify gravitational or spring, and maybe there is a spring in the question and there's also a height change, right? They mean both. They mean collectively both gravitational potential and spring potential. So if they just say potential energy, and that's all they say, that might be like the sum of both of those. Okay. Right. So you said, oh, right. Something else I want to say. I do remember when I went to college, I saw a little bit more nuanced version of this exact question. And here, I'm going to draw it up for you guys. It's possible if you go to college, they still have like the same textbooks. Here's a more nuanced version. Here could be your spring. Here could be your, well, I guess a block, some mass M, some spring constant K. Okay. And then sometime later, maybe it squashes to some maximum squash value. Right. I call this X. Right. And suppose this was like H, something like that. And then dash, something like that. Okay, so you guys get that, right? sometime later. All right, so you guys see that? Okay. So the setup would actually look like this. Sum of energy initial equals sum of energy final. Okay. Now there's a little bit ways to set it up, but you'll get to the same answer. Guys, this MGH only gets you to this dashed line, right? You guys see that? But then isn't it true that it continues to compress the spring and gravity's still pulling it down while it's compressing the spring? Right. So that's like more height loss. So the lowest point it actually goes is actually way down here. Okay, so the lowest point's actually way down here. Right. So its initial potential energy, I should say gravitational potential energy, isn't just mgh. If you define the floor way down here, isn't actually mg times h plus x. Right. So the setup would actually look like this: mg and then h plus x, and then that goes to 1/2 kx squared. Okay, so that's like the more nuanced version. Consider, well, while it's squashing the spring, it is still changing height, and gravity's still pulling it down. Okay, all right. So I gave you guys kind of a simplified version here. All right. Ooh, challenge questions. You guys ready for the challenge questions? All right, here we go. Ball rolls without sliding downhill length L. Now, without sliding is important because now there is friction. It's like static friction, but the static friction does not actually take energy out of the system. So it's not actually an open system. It just induces rolling, causes something called torque. Because these last two questions, well, actually, sorry, this rolling question involves physics that we have not gotten to yet. We haven't gotten to rotational dynamics yet. Right, so it's more of a feature type topic. What objects do you think to put in the system? Yeah, the ball, the earth, and the hill. That is true. Ball, earth, hill. Right. I'm including the hill because there is a force from the hill. Now you might think back to a couple days back. Well, hold on a minute. Wasn't there like a kid in a sled sliding down a hill a few days ago? And I did not include the hill. You guys remember that? Right. And there was a friction force from the surface. But I was treating this as an open system. I was saying that friction force was doing negative work on the kid in the sled. So it was taking joules out of the system. Okay, right. That's not actually the case for the ball rolling. Right. So I'm going to include the hill. There is a friction force from the hill surface, right? But it can still be a closed system. Okay, because it's only inducing rolling. Right. So what type of energy at point A? mgh. That's right. What type of energy at point B? Yeah, there's definitely some 1/2 mv squared. Right, like if you point a radar gun at, or if you have a speed gate, one of those speed gates that rolls through it, I'm going to call this translational kinetic energy. It definitely has some 1/2 mv squared. Right, but guess what? It also has exactly this rotational kinetic energy. You guys see this green one down here that we haven't even touched yet? Right? Again, that's a future topic. Probably in January we'll start looking at that. So I'm going to say plus 1/2 I omega squared. This I is like a rotational inertia. It has to do with how easy it is for something to roll. So if you have like the cylinder rolling versus if you have like a sphere that was rolling like a ball, those would roll differently, right? It's like if you push on a ball, how much inertia is involved with it rolling? It's hard to get it rolling, but once it's rolling, it's hard. So, hey, you guys ever ride a bicycle that has like little like 24-inch tires, and you ride a bicycle with like big old 29-inch tires, right? Can you feel the difference? Guys, those big old wheels, it's harder to get them rolling. But once they are rolling, it's also harder to stop the bicycle because they have like more inertia. Okay, so maybe that's one thing. Anyway, so how are we going to solve for? All right, and I threw you guys a hint here. Said omega is equal to v over r. Let me see if I can find something here. Something. Where's? Got it. Got it right here. Right. So here's from the future. Party, I'm from the future. We got this ball rolling down this hill. Here's conservation of energy. Hey, look, this is exactly the setup we just did. You see that? Right. Right. Then in place of omega, I'm going to do v over r. Right. You see from v over r. Right. And in place of that I, well, it depends on what kind of ball you have. Now, this particular poster, I have, guys, is a basketball like a hollow ball? Right. Like a spherical shell, you can think, right? Right. So there's a particular equation for this I for a spherical shell, like a basketball, which happens to be this. It's not necessarily all well. All right. And then you can solve for like how fast is it going at the end, like that. Right. So get that one, but we're gonna do a simplified version. So I'm gonna say mgh equals let's do 1/2 mv squared plus 1/2 I omega squared. We're just going to leave the generic I in there, so it could be any kind of ball, but then I don't really know exactly what I is, so I'll just leave it as I. Right. Again, if I knew if it was a basketball or a baseball, I could put that in terms of M and R, but let's say I don't know that. Okay, 1/2 mv squared plus 1/2. Okay, so we'll just leave it I as I, but this omega, all right, now this is something you guys do know. Guys, omega is equal to what again? In terms of V? V over R. Exactly, V over R. Where R is the radius of the ball. Right. This I is also proportional to R squared, but yeah, we'll say that for the future. Okay. So I got MGH equals, let me factor out this V squared right here. So I got a 1/2 M here. I got a plus 1/2 I over R squared here. And then I can factor out the V squared. Okay, so I can do that. Right. I got a V squared right here. I got a V squared right here. That's also being squared. All I did was I just factored that up. Okay. Huh? What's that? Why would okay, yeah, so this I here shows up as this I here. Okay. This R squared shows up as this R squared. Okay. All right. All right. I suppose I could take this 2 and cross multiply it. So here, let's do that. Do 2 MGH. Right. And then here, I'll do this. Right. M plus I on R squared. B squared. Okay. Right. Then I need to take all this in parentheses, divide it over, and then take the square root. And that's it. So V equals, okay, so I got this 2 MGH. I'm going to divide by, got M plus I over R squared. Right. And then the last step is to take the square root. That could be the answer. Right. Again, this could be any number of a type of balls. So if you have like this basketball, there's some rotational inertia associated with that. It ends up being 2/3 mr squared. So I could plug that in for I. If it was a solid ball, it would be like 2/5 mr squared. Yeah, if it was a solid cylinder rolling down, I could call it 1/2 mr squared. Right? So there's different values you can plug in for I. Right? But that'll tell you how fast it's going to the bottom. Okay. You guys good? All right, because we got one more. You guys ready for the last one? Oh yeah. What's that? No. All right. Last one. All right. So we got these 2 asteroids gravitationally attracting 2 asteroids. Now I told you guys you're gonna have to use this universal form of gravitational potential energy because this gravity field is always changing. Did I show you guys yesterday that? Oh, whoops, where'd it go? Well. I dig it real fast. Oh, come on here. You guys remember this from yesterday? Right. So if you start off with the universal form, you say, well, if this height change is tiny compared to the radius of the planet, it does simplify to MGH, which we use almost all the time anyway. Right. All right. So we're going to use the universal form right here. Because your AP Classroom, if you guys haven't got around to it yet, you do need to use this formula on AP Classroom. I think there's one question, I think, about this. So let's go sum of, let's do this first. Right. So it should be each asteroid. That's it. Right. So deep space, we got 2 objects, each asteroid. Right. And energy at point A, could I call that negative G here? Guys, all I'm doing is I'm just following this green box right here, right? If each asteroid has the same mass, can I just call it G M M over, and then there'd be radius A, right? Notice it's negative, right? Talked about that yesterday. Okay. So let me remind you guys a little bit why it's always negative. Okay. Because okay. Well, first of all, it worked in this form. It simplified to MGH anyway. Okay. But I don't have my escape speed poster. All right. I don't know where I put that. Okay. But when I was explaining escape speed, here, if I said if two objects were like at the other opposite ends of the universe from each other. Guys, this R could be like 1,000 light years or something crazy, right? Guys, what is 1 over 1,000 light years? That's very, very, very close to what number? 0, right? Kind of like 1 in a billion chance of winning the lottery. It's basically 0, right? So starts off 0 potential energy, but as they get closer together, it loses potential energy, it's losing height. So it's always negative. All right, that's negative. Right then, when it gets to point B, is that basically negative G M M on RB, like that, right? But also, guys, if those asteroids are now in motion, suppose they started at rest and now they're in motion, I also have to consider what? Plus 1/2 mv squared plus another 1/2 mv squared for each asteroid. Right? Isn't that the full setup right there? All right. Let's solve for this V. You guys ready to solve for the V? You guys are good so far, right? Everything's makes sense? All right, so sum of energy at point A equals sum of energy at point B. Okay, now point A, it's just negative G M M on radius A, so like the distance of separation. Okay, and I'm assuming they start at rest. Oh yeah, okay, it does say starts from rest. Okay, all right, that's why it's only potential energy. Right, then equals. Right, now where'd that energy go? Well, when they get close together, I got negative G M M on RB. Right now, guys, radius B is a smaller separation distance. Guys, if you divide by smaller numbers, your overall answer becomes what? Yeah, bigger. Right, and the fact that it's negative means it's overall a smaller value. Like, guys, if this was like negative 100, this could be like negative 150, maybe. Right, so there'd be a smaller value, right? Right, and then plus 1/2 mv squared for one asteroid on move, plus another 1/2 mv squared for the other asteroid also on the move. Let's say we're solving for this V right here. Right? Right, that gets so far? Right? Because that's the physics. Right? Can you set up the physics equation? Right? Actually, I think your AP classroom question has multiple choice answers sort of in terms of that, and then it just stops. They don't even have you solve it. They just say, like, can you figure out that far? Right? The rest of this is just the algebra. Right? Can you do the algebra? Right, so let's do this. Oh, here, I'm going to add this. But here, you guys probably solved this already for homework, right? So here, I'm going to add this over. So that looks like G M M on RB minus G M M on RA. Over here, I'm going to factor out all the. Actually, I can add these together because they have the same mass. So I'll just call it MV squared. Right, because they have the same mass, right? Right, then, oh, guys, let's get a common denominator. Can I do RA over RA and RB over RB? I can do that, right? Okay. So that'd be G M M, and then I got RA minus RB all over RA times RB. And then that's MV squared. Oh, guys, what can cancel out on both sides? Yeah, mass, right? So not completely. They're still a mass, right? But just the fact that they're the same mass, or even if you just know proportionally what they are. Like if you said one mass is like 2/7 of the other mass, right? As long as you know one mass in terms of the other mass, right? Right. Now, mass is still in the equation. It didn't completely cancel out. Right? Very last step. Can I take the square root? Right. So the speed they'll be moving after moving that distance from RA to RB. It's a giant square root. I got a universal gravity constant. I got, well, I know something about, about mass proportion. Okay. I got the difference in distance moved divided by RA times RB. Okay, there you go. That's exactly how fast each asteroid is moving. Okay. That makes sense.
Wait, Mr. Griffin, why do you have the radius on top of the, like, GM and the
Oh,
like,
here,
where did
okay.
that come from?
So this right here and this right here, I was just getting a common denominator. Right. So here, so it just started as GMM over R, right? And this was GMM over R. Okay. Right. And then I said, I want a common denominator. So I'm gonna multiply this top and bottom by RA over RA. This top and bottom by RB over RB. Because this fractionary circle is equal to 1, and this is also equal to 1. So it didn't change anything other than it gets me a common denominator.
You just add it over here.
I multiplied. Right? Okay. Okay, here, yeah, let's do a review here. Okay. So we'll just go back to what if here guys, what if we got this? What if you ordered a couple of pizzas, right? Right, you guys see you ordered a couple of pizzas, right? And in this box, maybe I have a quarter of a pizza left, right? So this is all eaten and gone, right? And then I got a quarter pizza. And over here I got something crazy. We got like a seventh of a pizza. Right. So this is like a quarter of a pizza, and this is like 1/7 of a pizza. Right. And you're like, I don't want 2 boxes. I'm just gonna put these all together in one box and throw it in the fridge, right? You guys get that? Right. Well, how much pizza do I have? Right. So the total pizza equals, let's say I got a quarter pizza over there plus a 1/7 of a pizza over there, right? Well, what is 1/4? I should have left some space here. Oops. Plus 1/7. I need a common denominator, right? How do I get a common denominator?
Multiply by 7 on that side.
7 over 7, 4 over 4, right? Because I'm multiplying by 1, it's not actually changing anything. I'm just getting a common denominator. Okay. So that's what, 7 on 28 plus 4 on 28. That's like 11/28 of a pizza that I have left. Right? 11/28, right? And that's all we did over here. Right? And so we just got variables. That's all. Yeah. All right. Yeah. All right. So you guys good? That's good. All right. Dig around here. But let's do a few textbook puzzles. You guys are good with the packet, right? The energy packet, right? Just throw that into the grade tray before you leave class today. I will give you guys points in the grade book for that. Yes. Oh, I forgot about that. Here, guys, real fast, the bet. These are just extra questions. I pulled these out of the honors textbook. No, I'm not assigning these, but if you wanted some extra questions to look at or say, hey, what does like honors physics kind of look like? That's what these are. Yeah, so yeah, these are just bonus questions. Think about it. Yeah, so don't worry about those. If you didn't do those, then yeah, that's okay. Oh yeah. Oh, did we not? Yeah, see, yeah, you can probably saw that, right? Just put that equal to that and buffer B. Okay. All right. Right. Weightlifter. I was doing this again. Okay. All right, guys ready for 8 weeks? All right, chapter 5. A weightlifter lifts a 350 Newton set of weights from the ground level to a position over his head. Now, guys, pause right there. Let's put those numbers in context. It's 350 Newtons of weight. How many kilograms of mass is that? 35? Is that like 35 of these? Guys, if I put 35 of these like in a grocery bag and you look at this, that's what we're talking about, right? All right. All right, to a position over his head, a vertical distance of 2 meters. How much work does the weightlifter do? Ooh, here's an interesting note. Assuming he moves the weights at a constant speed. Right? Because now, this is a really nuanced detail, but if the weights start from rest and he's accelerating them, he would be lifting with a higher force than the actual weight, kind of like the elevator physics, right? And he'd be maybe giving the weight some motion, and that would be kinetic energy. We're not going to consider any of that. We're just going to do the real simple version of this. All right, so here, I'll do this with you guys, or at least I'll set it up with you guys. So, weightlifter, how much work does he do? So work, guys, could work be equal to what times what? Force times distance. And the force, is it okay if I do the simple version of this? The force is just basically equal to the weight, right? Right. Because here could be your weights. Right? If I do a free body diagram, I got mg pulling down. Okay. Let's say the F lift is just balancing that out. That's what the constant speed is about, constant speed, because I can say this is equal to this. This is F lift. We'll just say it's equal to mg. Okay. And guys, the distance that he lifts, isn't that just like a height? Oh, look at that. The work he did lifting it is equal to the potential energy they end up with by the time he's lifted them up. Right? It's the same thing, right? You guys see that? Okay. Number 4. A shopper in a supermarket pushes a cart with a force of so many newtons at an angle 25 degrees below the horizontal. The force is just sufficient to overcome various frictional forces so that the cart moves at constant speed. Because when you see that constant speed, what do you know about the net force on the cart? 0, right? Now there are multiple forces, but the net force is 0. Right? What do you got here? Find the work done by the shopper and but they didn't ask about net the work done by this friction, but we can do that too. And then what is the net work on the cart? Why? So I do have a poster exactly for that. Here it is. Right. So yeah, that question exactly actually inspired this picture. Here's exactly what's going on. Right. So you're pushing with some force at some angle below the horizontal, exactly like that, right? Okay. Now, guys, here's all the forces. Got this force. The shopping cart has some weight, right? And there's also a normal force. Guys, which force is bigger, the normal force or the weight? The normal force. Guys, why is the normal force much bigger than the weight? Yeah, the fact that you're kind of pushing downish. There's a downward component to the pushing force. That plus the weight is the total downward force. And the normal force has to balance that out. So, guys, let's just I'm going to make up some numbers. Suppose I'm going to make up my own numbers. Guys, suppose this is 50 newtons of pushing force. You guys got 50 newtons? What if this is a 37-degree angle, which means I'm setting up a 3, 4, 5 right triangle? So, guys, if this is 50 newtons, could this be 30 newtons? And this could be 40, right? Yeah. Okay, so I got 30 newtons here. Suppose I got, I don't know, 10 newtons here. Guys, what's this 30 plus this 10?
40.
40. Therefore, what's the normal force? 40 newtons, right? Okay. Guys, suppose you had a coefficient of friction of 1. Maybe you got like a sticky floor. Somebody just spilled all the syrup. Oh no, got a coefficient of friction of 1. Right? Guys, if this is 40 newtons, what would the friction force be? Also 40 newtons, right? Because 40 times 1 is 40. Coefficient of friction is 1. Okay. Could this 40 newtons balance out this 40 newtons? Yeah. And that could put the cart at constant velocity, couldn't it? Now your textbook gave you different numbers, but it's the same idea, right? Okay. All right. So the work that the shopper the shopper does pushing the cart is just this component of force, which is the 40 newtons forward, right? Times however far you push it down the aisle. And your textbook said however many meters that is, right? Okay. So, or the other way to do it is the total pushing force times the distance moved times the cosine of the angle between those two. But that gives you the same thing. Okay. I just said, let's take the cosine component of the pushing force first. Same thing, right? Okay. Right. Guys, here's another detail. Notice that this angle is the angle between those two vectors, the pushing force and the displacement forward move. Right. Notice I did not give you this angle down here, which would be complementary to that. Sometimes you'll get that angle instead. Guys, if you guys got this angle down here, this would no longer be a cosine. It would be a what? A sine, right? So careful for that. Right. Right. Okay. So you guys okay with the right? Now, guys, suppose you run the numbers and let's say you put in 100 joules pushing the cart forward. Put in 100 joules pushing it forward. Right. But the cart didn't speed up at all. Right. How much work did the friction do on the cart? Negative 100 joules. I put in 100 joules pushing it forward. The friction did negative 100 joules of work, taking that straight out. So what was the net work done on the cart? 0. You guys think you can solve your textbook question with just different numbers? Yeah, it's the same question, right? Right, next one. Starting from rest, a 5-kilogram block slides 2.5 meters down a rough 30-degree incline. Ooh, you guys imagine an incline, right? There's friction. The coefficient of kinetic friction is this number. Determine the work done by gravity force, the work done by the friction force. Right, guys, is the work done by gravity probably a positive work, speeding up the block? Is the work done by friction probably a negative work, taking joules away from the block? Right. Oh, what else we got? The work. Oh, the work done by the normal force. Guys, if you're sliding across a surface, what is always the answer to that question? The work done by the normal force is always what? Zero. Kind of like because the block sliding parallel to the surface and that normal force perpendicular to the surface, the dot product is always zero. That normal force is not doing any work. Okay. No, the only way the normal force might do work is say if you were in an elevator and it was like moving up, right? That's not what this is. This is sliding parallel to the surface, right? Qualitatively, how would the answers change if T had a shorter ramp, a steeper angle, same vertical height? Ooh, that's an interesting question too. Right? Of course, you guys know all the answers are posted, so you guys can check that. All right. 24. 2 blocks connected by like string over a pulley. All right, and there's a spring here. This block on the left is heavier than this block on the right. If the system is released from rest, the spring is initially not stretched. Find an expression for the maximum displacement D in terms of all right. Of M2, because M2 is going to move up, right? Right. Now, there's different ways they could have gone with this question. Make sure my questions are in order here. All right. There's different questions they could have asked, which would lead to different answers. And there's a reason that this particular question, how it's phrased, is in the energy question. So I'll help you guys out with this a little bit. All right. So we got block M1 here. Got string. Got block M2 here, which is smaller. And then a spring, some constant K, and then the ground. Right. Pulley, ceiling. Right, so that's the setup, right? Let's set up a conservation of energy. So sum of energy initial equals sum of energy final. Okay. You guys think this block 1 is going to fall down some distance? Did it say D or H? I don't know. All right, I'll just pick one. Let's go D. Okay. And this block 2 is going to move up exactly that same distance. And the spring is going to stretch exactly that same distance too, isn't it? Ooh. Huh? Yeah, right. Okay. So guys, what's the supply of energy? Yeah, M1, G, D falling. And that goes into 2 things. It's got to lift the small block, M2, G, same distance up. Okay. And it also has to do what? Stretch the spring. There's your 1/2 K D squared right there, right? Right. Now, guys, if you play forward, do you think this is going to oscillate like right? So you can just go back and forth. So guys, this D is the maximum stretch value. And I know that because there's no motion. I didn't put anything about kinetic. So this is the maximum stretch value, right? Guys, they could have asked a different question, which is what's the equilibrium stretch value? Do you guys think, suppose this goes back and forth like 100 times and eventually kind of settles down some point? Here, guys, last question today. Is the amount that the spring is stretched at the equilibrium point less than, more than, the same as the maximum stretch? Yeah, less than. So it's stretched, but not as much as D. And with that, you use force equilibrium, which is a different setup. But bell's about to ring though. All right, so guys, you guys gonna finish AP Classroom by Wednesday morning, right? All right, I'll see you guys Wednesday morning. You guys have a good weekend.